Hi, everybody. We're going to go over what functional groups are and how to name compounds that have these functional groups. So functional groups are a form of substituents, and we're going to go into these definitions first, and then I'll show you some examples, and then we'll go into how to name them. Now, this is a video that is going to give some explanations and give some examples on what these functional groups are and how to name the compounds which have these functional groups in them. So there's going to be a full rundown of the entire list of functional groups and their suffixes and how to name the compounds, going through every single functional group really fast in my next video. So this video is more the theory. This is the explanation. So you can just kind of get the gist of what is going on. And then go to my next video and I'll go through all of the, naming all of the compounds with functional groups in it very quickly now that you've seen this video and know, what I'm talking about and why. So let's start. So if you remember from the previous video, we were going over naming hydrocarbons. And remember, hydrocarbons are just the long chain of carbons, for however many carbons it goes on. Carbon, 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 carbon. And on each of these carbons, the carbons are going to have 4 bonds. So whenever they're not connected to another carbon, like this carbon is connected to this carbon, we are going to automatically assume that this carbon has these 3 hydrogens attached to it, right? And this carbon right up here is going to have 2 hydrogens attached to it to make up the 4 bonds that carbon has to have, and so on and so forth. This is going to be 2 hydrogens. All these sandwich carbons in the internal part of the chain are going to have these 2 hydrogens on each of them, and then the ends are going to have 3 hydrogens. So the carbon always has 4 bonds, right? So this is a hydrocarbon because hydro, hydrogen, and carbon, obviously carbon. And that's all these are. It's just these long chains of carbons with hydrogen sticking out, right? Now, these hydrocarbons can come in one of these 3 forms. There's alkanes, alkenes, and alkynes. And the only difference these have from each other are whether or not the carbons are all connected to each other through single bonds. So this would be single bonds. Or an alkene is a double bond. So that would be also known as a pi bond. And alkyne is a triple bond. So an alkane, anything ending in ane, an alkane is going to have carbons just connected by single bonds, just like the one I just showed you up here. Alkenes is going to have a double bond. It's going to end in ene instead of ane. Okay, and then the alkynes are going to have a triple bond somewhere along the line in that carbon chain. Okay, just a little brief refresher. So these hydrocarbons, if they have an alkyl group on them, that means I'll just draw an alkane for an example. Say we have that, okay? But then we have coming off of it another group of a couple carbons, a carbon chain, a couple carbons in a row there. And so now this means that this carbon right here is not going to have 2 hydrogens coming off of it because one of where the hydrogen would normally be, it has this extra substituent sticking off of it. So it's only going to have 1 hydrogen coming off of this one, remember? And so we're naming these with using these alkyl groups. And if you remember, 1 carbon, 2 carbons gives you the prefix ethyl, because see the YL because it's an alkyl group. The rest of this is, let's see, 1, 2, 3, 4, 5, 6, 7, 8 carbons, which starts with oct. So ethyl octane. But then we need to write the carbon number where this ethyl group is coming off of. So 1, 2, 3, 4. That's carbon number 4. If we were to number it backwards, 1, 2, 3, 4, 5. So we always want to give it the lowest number possible. So this is going to be 4 ethyl octane. Right? Okay, so now we know what alkyl, we're remembering what the alkyl groups are, right? It's the extra shorter chains of carbons that could come sticking off of this long hydrocarbon here. And so that's a type of substituent, because a substituent is anything that takes the hydrogen away from that carbon by replacing it with some other chain. So that some other chain is what the substituent, that's what is the definition of substituent. So the alkyl groups are these just another shorter chain of carbons and hydrogens. So it's not the main hydrocarbon. This long one would be the main hydrocarbon, but the shorter hydrocarbons are the alkyl groups. Now, functional groups are when it's not just a hydrocarbon chain. Functional groups are when something is coming off of the main hydrocarbon chain. It's not just carbons and hydrogens. We could have an oxygen there with a double bond, or we could have an OH here, a hydroxyl group coming off of the other thing. And so in this one, this would be the only carbon in this functional group. The other parts would be the oxygen over here connected with double bond, and the oxygen and hydrogen over here. And as you can see, since this carbon has a double bond connected to it here and a single bond connected to the oxygen over here, and then it's connected to the hydrocarbon long chain, that's already 4 bonds. So this carbon is going to have no hydrogens. So the only difference between the alkyl groups and the functional groups is that the functional groups has other stuff on it, not just carbons and hydrogens. It has other stuff. It has carbons, and it could have oxygens and other especially electronegative atoms. It could have bromine on it or whatever. So functional group is just the same as an alkyl group, but it is not only limited to carbons and hydrogens. Okay, so as we were saying in the previous screen, functional groups are when you have some sort of a hydrocarbon, and instead of one of the carbons in the hydrocarbon, in the alkane, remember this is an alkane because it's all single bonds between the carbons, right? Here's a carbon, here's a carbon, and these are all single bonds between the carbons, right? So one of the carbons, this one, just randomly I picked, instead of having the hydrogens that fill up the 4 bonds that it needs, one of the hydrogens is left out because instead of the hydrogen, there is some sort of other um, carbon chain that's sticking out as a substituent from this original hydrocarbon, this alkane that I drew. So a functional group takes away one of those hydrogens, and instead it's replaced by, and this is just one example of a functional group. You could have a functional group coming off that is just bromine, like that, or you could have a bromine and let's see, another carbon coming off of there like that. And so this would be carbon, carbon. And in this one over here on the left, you would just have the one carbon connecting the O and the OH. So the point is that the difference between the functional groups and just the regular alkyl groups is that the functional groups has other stuff other than just carbon and hydrogens. It's got other elements in there. Okay, that's the only difference between the functional groups and the alkyl groups for substituents. Remember, these are all under the umbrella of the definition substituents. Substituents is anything that's sticking out, any other chain of something, not the hydrogens, but any other chain of anything else sticking out from the original hydrocarbon. Cool? Okay, so the first functional group I want to tell you about is carboxylic acid. Carboxylic acid. So we have some sort of an alkane here, right? Or, it could be an alkene or an alkyne. But anyway, this is a hydrocarbon, right? This is the parent chain. This is the long hydrocarbon chain. And so a carboxylic acid would come down, have a carbon right here, carbon, and then one side a double bond with an oxygen, and the other end a single bond with an oxygen and a hydrogen. And you could also draw this. Double bond oxygen. You could draw this O and then a single bond to H, a single bond to hydrogen. This and this is the same thing. It's just that the OH and carboxylic acids are always appear together. So as I said before, scientists are lazy. So if we can get away with drawing something faster, we will. So we just go OH. But you're going to see it either way. So when you see a substituent coming off of a hydrocarbon, whatever this is, I'm just going to do that blah, 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 blah for the hydrocarbon right now because it doesn't matter. So the point is that you're paying attention to what's coming off of the hydrocarbon. So we have one carbon here and then a double bond with an oxygen and a single bond to an OH. So this right here, see, this is the only carbon. This right here is a carboxylic acid. Carbo, like carbohydrate or carbon, but it's XYLIC, carboxylic acid. Or sometimes we call it the carboxyl group. If it's just the C and the O inside of a carboxylic acid, if we're just referring to the C with the double bond to the O, we call this the carboxyl group. Because this C double bonded to O is what makes the difference, is what makes it a carboxylic acid, as opposed to just a C and an OH. Because see, then this would have to have 2 hydrogens coming off of it. And so if it's just an OH, that's going to be an alcohol. So what makes it not an alcohol and instead of carboxylic acid is this carboxyl group that's also attached to the exact same carbon, the alcohol the OH is attached to. So if it has just an OH, it's an alcohol. But if it has an OH and also the carbon the OH is attached to is double bonded to another oxygen, then that is a carboxylic acid. And the carbon with the double bond to the oxygen, which is what makes it a carboxylic acid, is the carboxyl group. Make sense? So then if here's the little squiggly line that represents the hydrocarbon, it doesn't really matter the structure of the alkane or the hydrocarbon right now because I'm just showing you the functions that come off. If like, okay, so let's say right here is one of the carbons for the hydrocarbon, right? And off of one of those carbons comes a double bond with an O, not an OH, because that would have to be a single bond, but an O, a double bond to an O. And then it goes on for the rest of the thing, it's something else. Like we could have whatever is coming off of here, it doesn't matter. And the left side in this double bond to an oxygen is something else. So we could have other things coming off of it too. It doesn't matter. Okay. So what we call these, the rest of the molecule, and here's on the right, there's the rest of the molecule over here, because what we're focusing on is one carbon being double bonded to oxygen. And then it goes on, boop, 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 and it comes from boop, 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 some other place. Okay. So the rest of the molecule, we're just going to write R for the rest of the molecule. and then we're going to go C, which is double bonded to oxygen, and then we're going to have another single bond to another R, and we're just going to put a little prime there just to differentiate between this R and this R, because they're two different parts of the molecule, so they're not going to be identical. If they're identical, then we just write it R, R, like that. But they don't have to be identical. So we're just going to put this little prime here to show that these can be two different sections of the rest of the molecule. Okay, so, or we usually say, we'll say sometimes COR, because that's this section right here. So we all know everything has an R over here at the left side. The carbon's got to come from somewhere. There's a rest of the molecule is going to be over here. Okay, so it's always R over here. But so we just write the COR, or we'll go dash COR, just to show that the carbon's single bonded to something. It just doesn't matter what it is. Okay, so COR, which means the carbon has a double bond to the oxygen, and its other bond is to the rest of the molecule, and then here it's coming from somewhere. Okay, so the COR that we're talking about is called a ketone. Now, not key is in a key to your door, or key on the piano, or key in music. Not key like that. A ketone, Ketone, ketone. But I always remember it because if you want to sing in key, you have to have a good core, right? So although that's not the right spelling for it, I just remember that it's COR, core, means ketone. Okay, now next, one of the carbons in this hydrocarbon has, again, a double bond to an oxygen. But then the very next thing they're bonded to is another oxygen, but that's a single bond. And then it goes on into the rest of the molecule. So you would have the carbon that's in the hydrocarbon chain, double bond to an oxygen, then bonded to an oxygen, and then the rest of the molecule. And of course, it's coming from the rest of the molecule over here on the left. So we're just going to put a little prime there just so we can differentiate that these are two different parts of the molecule. They're not identical. But so if you look, this is how I can tell the difference between this and the ketone. Because remember, the ketone is core, right? COR, core. So that's a ketone. Because in order to sing it on key, you got to have a good core. Okay. All right. So the difference is this has COOR, and this is coming from the rest of the molecule, COOR. Okay. Yeah. One of the O's is double bonded to the C up here, and the second O is single bonded to the C down there, and then it goes on into the rest of the molecule. So COOR. This is called an ester. Now, not Easter. That's EASTER, like the holiday. It's not Easter, it's ester. And you'll find this on, probably you'll find this on your vitamin C bottles at home. If you have vitamin C at home that you take, or any kind of vitamin that has vitamin C in it, you will probably see this word ester alongside a whole bunch of other words that goes with it. But ester is COOR, as opposed to ketone just means COR. So the key to singing on key is having a good core, COR core. But, and this is how I remember ester, but my uncles always drank Coors beer when we got together for Easter. We'd get together and have a big barbecue. My uncles would always be drinking beer. They actually drank a different brand of beer, but this is how I remember core, COOR, is ester. And it's just no A is in the correct spelling of ester. But on Easter, my uncles would get together and they'd drink Coors beer. And so that's how I remember ester is COOR attached to something else. And it has to be the C double bonded to oxygen on one sticking off of the C, and the next part of the C is an oxygen single bonded to the C, and then it goes on to the rest of the thing. Now, you might wonder, well, but Suzanne, you just showed us saying a C double bonded to the O and then single bonded to an OH is a carboxylic acid, right? This is the carboxyl group, and the carboxylic acid is a C double bonded to an O and an H. Isn't that the same thing? Because look, check it out. This would be an O, and then the H would be the rest of the molecule, wouldn't it? Okay, so yes, technically, a carboxylic acid is also classified as an ester. But if you have the OH instead of the R, instead of a whole bunch of other stuff in the rest of the molecule, or just a different element, if you have the H instead, that's when it is a carboxylic acid. But if you have something other than an H, anything but H, hydrogen, then that is when it is an ester. So remember, your uncles drink Coors beer on Easter. So a COOR is an ester. Okay, so I hope that is helping you remember all these and be able to keep them apart a little bit. Okay, so another similar functional group is when there is an oxygen in the middle of two other sections of its molecule. So when you have the rest of the molecule over here, and then is bound, has a single bond to it, to oxygen, and then oxygen in turn has a single bind to it, to the rest of the molecule, the other rest of the molecule over here. And remember I said that you don't really have to usually write that first R, you can just write a dash, so or, because we all know that never changes. There's always the rest of the molecule over here to the left, right? So we don't really need to write that down. So we just go dash OR, and the OR is just, it's implied that it's a single bond to each other. Well, this is called ether. This is an ether. When there is, part of the molecule, and then it binds to an oxygen, which binds to the rest of the molecule. So this would be the R, and this would be the R prime, right? So it's just or. And I remember this one, to keep it separate from the ester and the carboxylic acid, to keep them all separate. I remember ether because it's either or. Get it? Either or. And either in that sense is spelled like that. Either or either or. But the either or reminds me that when it's just an or, then that's going to be ether. It's not going to be ester, because ester is COOR, right? Because on Easter, my uncles get together and drink Coors beer, COOR. And a ketone, the key to singing on key is to have a good core, COR. So this is just OR. So that's ether. So either or is how I remember it, either or, and that's called ether. Now, this whole time I've been talking about carbons double bonded to oxygens and carbons single bonded to oxygens. So how do you tell when a carbon is supposed to be double bound to an oxygen or single bound to an oxygen? Because see, like here's the carboxylic acid over here, and the carbon is double bound to this oxygen, but it's only single bound to this oxygen. Why is that? Well, let's go back, and I went over this in the intro videos. Let's go back to the periodic table. I just put this little corner of the periodic table right here because we're dealing with oxygen, which is right here. And remember, when you're dealing with, in organic chemistry, when you're dealing with these elements over here, it's however many columns they're back from the end column. Like here's the end column. So we count backwards, 1, 2, and that's the column oxygen is in, right? So this would be 1, 2. So oxygen is going to get 2 bonds. Just like if you were to count backwards all the way to carbon, 1, 2, 3, 4. Carbon is in that 4th column back from the end. So that's why carbon always gets 4 bonds. And those hydrogens have to go in and fill in all the missing bonds that carbon needs when we're dealing with the carbon chains in organic chemistry. So oxygen gets 2 bonds, always gets 2 bonds, right? So if you check this out, the carboxylic acid up here, this oxygen is only bound to carbon, right? There's nothing coming off of this oxygen to something else. It's a dead end. It's a dead end street. It's just bound to carbon and then ends. So in order for oxygen to have its 2 bonds that it needs, we have to give it a double bond with the only thing it's bound to, which is carbon. If you look at this oxygen down here, this oxygen is bound to a hydrogen over here on this side. So it only needs a single bond over here to be bound to carbon because it has 1, 2 bonds to it. And the same goes for down here. What is this again? COOR. So that's ester, right? Because my uncles get together on Easter and drink Coors beer. So COOR. So that's an ester. So this oxygen, again, up here, it's the same deal. This oxygen is dead end. It's only bound to the carbon. So it needs 2 binds to the carbon. But this oxygen over here is bound to the rest of the molecule on its right. So it only needs one single bond to the carbon. Does that make sense? And it also should be noted here, we're dealing with, remember when I said in my previous videos, oxygen is in the 6th column in group A, right? So that means oxygen has 6 valence electrons. So when it's double bound to a carbon, you're going to have 2 lone pairs, 1, 2, 3, 4, because the other 5, 6 is taken up by the double bind to the carbon. But remember, it's a dead end. There's no other bonds or anything to it. So the rest of its valence electrons, the rest of those 6 valence electrons have to be lone pairs. And so a lot of times you'll see compounds with the lone pairs drawn in on them. Usually if they're important, they're going to be drawn in. Or if you're taking a test, you probably want to draw in the lone pairs. And now see down here with this oxygen bound on one side, here's one bond, right? And here's the second bond. So it has its 2 bonds. And so 1 electron of the oxygen is taken up by the first bond. The second electron is taken up by the second bond on the right. And so it still needs 4 more electrons to get that 6. And then if you want to go into the octet rule says you can count the other group's electron that something's bonded to, which gives it the whole 8 for the octet rule. Okay, well, so far we've done 5 different functional groups. This top one, you can tell by the terminal group here. Terminal just means it's on the end, is OH, and there's nothing else. The rest of it is just a hydrocarbon chain. So that means it's an alcohol. The next one down, we have the same thing as we had with the alcohol. We have the oxygen single bonded to the carbon, and then hydrogen bonded to the oxygen. But then we also have this carboxyl group here, this carbon double bound to an oxygen, which is like a dead end street. The oxygen just stops. There's nothing after that. Unlike the OH, the hydrogen is attached to the oxygen. So with this carboxyl group, in addition to the alcohol OH, this is a carboxylic acid. This third one down is just a hydrocarbon chain, but then it has this, again, the double bond to the oxygen here, but this time it doesn't have the accompanying alcohol, the accompanying OH with it. So it's not a carboxylic acid. So if we remember, this C right here is bound to the O. So we know we're going to have a C and an O. And then after that is just the rest of the molecule. So that's an R. So core, C-O-R, remember the key to singing on key is you have to have a good core. So this is going to be a ketone. Now the fourth one down, it has, again, that double bond to the oxygen, but instead of it going off in an OH like it did with the carboxylic acid, or instead of it just being by itself to form the COR for a ketone, it's also bound to another oxygen that's in the chain. And so if we look at this, this is the C, this is where the carbon is. And so we're going to have a C, and then we have this O it's double bound to, so O, and then there's another oxygen that the C is bound to, so O, and then we have the rest of the molecule, R. So COOR, my uncles get together and drink Coors Light beer on Easter. So this is an ester. Now the very bottom one, we just have one oxygen in the middle of everything. So this is not going to have a carbon to it. You know, like this starts with a C, this starts with a C, because we have this carbon right there that's kind of the junction for these other atoms that are attached. But this one doesn't have a C to it. It's just the oxygen that's actually embedded in the hydrocarbon chain. So we have this oxygen, an O, and we have the rest of the molecule, R. So remember, my trick to remember this is either or, right? So this is ether. All right, so let's see if we can draw something for these. So here's a hydrocarbon chain. It doesn't really matter how long it is right now in this instance, in these instances, because we're just focusing on the functional groups. So we'll do hydrocarbon chains for everybody. Hydrocarbon chains for everybody. Hydrocarbon chains for everybody. Okay, so for an alcohol at the top here, what do we need for an alcohol? We just need an OH. So we can put it on the end here, or we could put it on one of these peaks, or like here in the middle. Okay, or up top here. Anytime it just has a substituent with an OH and that's it, that's all the substituent is, just OH, it's an alcohol. Now the next one, carboxylic acid, is going to have to be either on the end here, like we have a double bond to oxygen, and then we have an OH coming off of it, or if it's going to be in the middle somewhere, you have to have another carbon, because the carbon has to be double bonded both to the oxygen and to the OH group. And if you try to put that in the middle of the hydrocarbon chain, what happens? See, like here's the C, we're going to double bond it to the O, but we can't draw another line out here and go OH. Why? Because carbon has to have 4 bonds and 4 bonds only. And so this would be 1 bond on the left, second bond on the right on the hydrocarbon chain, third bond for the OH, and then fourth and fifth bonds with the double bond to the oxygen. So see, that doesn't work out. You can't do that. So you'd have to have another carbon initiating the carboxylic acid if it's sandwiched in the hydrocarbon chain, or it would be a terminal thing at the very end of the hydrocarbon chain. Now let's do a ketone. So remember, the key to singing on key is you have to have a good core. So the C would be right here, core for core, and we would have it double bound to an oxygen, and then the rest of the molecule. So COR, core, for ketone. Now ester, remember on Easter, my uncles get together and drink Coors. So you would have to have a C here and a double bond for the first O. But then this carbon, this can't be a carbon. This has to be another oxygen, because we need 2 oxygens, remember? And it's got to be embedded in the hydrocarbon chain, because you have to have the R for Coors for the rest of the molecule, or for COOR. Now the very last one, ether, remember either or? So you're going to have R for the rest of the molecule, and it has to start with an O. So we got to have this O, this oxygen embedded in the hydrocarbon chain, just like we had to do for the ester. And if you have any questions about this, or it doesn't make sense, if there's something I can clarify, please leave a comment and ask your question. I'll try to answer any questions that's sent to me. Okay, so now we're going to get into how to name these functional groups. And I just want to remind you that my next video is going to be the full rundown of the entire list of functional groups. But right now, we're going to follow through with the examples I've already given you of the functional groups, so you can just kind of get the gist of what's going on here and how these are being named. Naming functional groups. Okay, so first we started out with hydrocarbons, right? Hydrocarbons, because there's hydrogens surrounding a carbon, and the carbons are in a chain, right? So just this plain old hydrocarbon, that would be an alkane, A and E, because it's all single bonds, right? So single bonds. And then there are alkenes, because there's a double bond. And then there are alkynes, because there's a triple bond. And so, and let's just take the simplest one, the alkane, for these examples, and then we'll get into prioritizing double and triple bonds in a little while. But let's just take an alkane for the example. So you have an alkane, which is just this. They're just all single bonds, and this is a hydrocarbon chain. But then if you have something coming off of it, you have a substituent. And these substituents are called alkyls. And they're shorter hydrocarbon chains, see carbon, carbon. They're shorter hydrocarbon chains than the parent strand, but they're still hydrocarbon chains. Or coming off of this main hydrocarbon, there could be a functional group. Okay, and so this is going to be a functional group, because the difference is these regular alkyls are only carbons, carbon, carbon, with hydrogens filling in until each carbon has 4 bonds to it, right? So that's just a plain old alkyl. It's just a shorter hydrocarbon chain, and the hydrocarbons are just a chain of carbons with hydrogens filling in, right? So an alkyl is just another shorter hydrocarbon chain attached to the longer hydrocarbon chain. But then you get into functional groups where there's only one carbon, in just for example in this one, and there are other atoms as part of the molecule. It's not just carbons and hydrogens anymore. So that's what makes a functional group. So technically, a functional group is a type of alkyl, because an alkyl is anything that attaches to the parent chain. So you have to get rid of one of the hydrogens, because instead of having 2 hydrogens for the 4 bonds, the carbon only has 1 hydrogen to make up the 4 bonds, because it has this extra group coming off of it. So that's anything like that is an alkyl. So a functional group is a type of alkyl, the type of alkyl that has other atoms, and not just carbon or hydrogen. So if you look at it this way, we start off with hydrocarbons. That's the skeleton of the whole thing, of the whole compound, is the hydrocarbon, and that's the parent strand, right? And coming off of that parent strand are substituents. And what are substituents? But substituents are alkyls. See, that's why the equal sign here. Substituents are alkyls. Like substituents, hydrocarbons aren't necessarily substituents. The hydrocarbon can be the parent chain, the skeleton of the whole thing. But all substituents are hydrocarbons. And substituents coming off of hydrocarbons are called alkyls, because they make you take away a hydrogen in order for it to fit on there on the carbon, because the carbon has to maintain only 4 bonds to it. Now, out of alkyls could be one of 2 things. An alkyl could be a shorter hydrocarbon chain where it's just another couple of C's with H's coming off of it, or the alkyl could be a functional group. And the functional group is the one that has other atoms like oxygen and phosphorus, stuff like that. And it's not just carbons and hydrogens. Okay, so here's a good example. We have heptane, right? So let's look at this top one right here. Heptane, what does that mean? Okay, well, the ane means it's all single bonds of carbons bonded to each other. So it's going to be carbon, 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 carbon. So, and then the hept means that's going to be 7 carbons in a row. So 1, 2, 3, 4, 5, 6, 7, right? And again, you don't have to draw the dots when you draw these. I'm just drawing dots so you can see how it is that I'm doing this. So 1, 2, 3, 4, 5, 6, 7. Now, 3-ethyl heptane, let's go to the second one right here. 3-ethyl heptane, well, let's look at the end, let's look at the root of what this is. This is going to be the parent strand. This is going to be the skeleton of the whole thing, is a heptane. Well, we just did a heptane up here, right? So it's the same thing, 1, 2, 3, 4, 5, 6, 7. So that's a heptane. And then we look at this, ethyl. So the YL at the end of it means it's an alkyl, a substituent coming off of one of the carbons in this hydrocarbon. And the eth means that that hydrocarbon chain, the short hydrocarbon chain coming off of here, is going to be comprised of 2 carbons. 2 carbons, single bonded to each other. So somewhere on this hydrocarbon chain is going to be this connected to it, this ethyl group connected to it. Now, where at on the hydrocarbon chain is this ethyl group connected? Well, it's at carbon number 3. So 1, 2, 3. So we're going to bond to that first carbon in the alkyl group. There's the first carbon, and then here's the second carbon. There's the first carbon and second carbon, and here's the first carbon and the second carbon of the alkyl group off of this heptane. So 3-ethyl heptane means that's what that is. Or you could draw it this way too. It doesn't matter. Okay, now let's look at this third one down here. 3-ethyl heptanoic acid. Okay, so I'm just going to walk you through this, and I know you're not going to know how to do this yet, so just follow my lead, and then I'm going to explain why this is the way it is. Okay, so we still have our heptane. Our heptane is right here. But you notice we dropped that E from the heptane, and now we have oic acid at the end instead of the E. And so we know there's a heptane is the skeleton chain that makes this whole thing go around. 1, 2, 3, 4, 5, 6, 7. Okay, so that's our heptane. And there's a 3-ethyl, just like the second one right here. Okay, so we know at 3, we're going to have an ethyl group come off of there. And then it says oic acid. So this is carbon 1, this is carbon 2, this is carbon 3, this is carbon 4, carbon 5, carbon 6, carbon 7. Well, so an oic acid means that it is a carboxyl group. Remember, you have like this carbon here, and an oxygen is double bonded to it, and then the other thing bonded to it is an OH group. That's a carbolic acid. And then before that is the rest of the molecule. So this is a carboxylic acid. And so carboxylic acids need to be at the terminal carbon of this molecule, of this compound. And the terminal just means the end. Okay, so it could be at either the carbon 1 or the carbon 7, but you always put it on carbon number 1. If you have a carboxylic acid, it always goes on carbon number 1. And when it's a carboxylic acid, it's the terminal end of a molecule. So that's going to go, here's the double bond to the oxygen, and here's the bond to the OH group. Okay, so that is going to be 3-ethyl heptanoic acid. All right, now let's look at the bottom example here. 3-ethyl heptane 5-ol. Or you could also say 3-ethyl 5-heptane-ol, heptanol, 5-heptanol. You can do it that way too, and that kind of rolls off the tongue better, don't you think? 5-heptanol instead of heptane 5-ol. So 3-ethyl 5, because you always separate the numbers from the words with hyphens. So 3-ethyl 5-heptanol. Same thing as the 3-ethyl heptane 5-ol, same thing. So we have our heptane, 1, 2, 3, 4, 5, 6, 7. And we know there's an ethyl group at carbon number 3. So here's the ethyl group. And then at carbon number 5 has to do with this new ending, the ol. Because see, we dropped the E from the heptane and we put OL instead. So what does that mean? Well, if it's ol, that's the ending of alcohol, isn't it? Right? So that's what the ol means, the ol ending means. So at carbon number 5, we're going to have an OH group because alcohol means there's an OH functional group coming off of one of the carbons. Which carbon? Carbon number 5. Okay, so here is a rundown of the examples I've already gone over. We have alcohol, carboxylic acid, a ketone, ester, and ether. And just like we just did previously with dropping the E off of the heptane and then replacing that with a different suffix like ic acid for carboxylic acid, ol for alcohol, we usually use, in the case when we need an ending like ic acid, in the case where we need that word to flow a lot better, if like when we made heptanoic acid, here's the heptane, and we dropped the E, but we don't want to go heptanic acid. That sounds weird, right? So we want to use an O as a connector vowel to connect the heptane section from the ic acid section. So we want to use O, so we go heptane, and we dropped that E and replaced it with the O, and then we put ic acid at the end in the case of having a heptane with a carboxylic acid at the end of it. So let's go over these suffixes that we're going to use for each of these 5 things. First, for alcohol, we're going to use that ending OL. Now, we don't need to use an O as a connector vowel in this instance because we already have an O in the suffix right there, OL. So in the case of the heptane that we just did, it would be heptanol, right? So let's look over here at our examples, at our example molecules, and let's name this. Okay, so we have 1, because we want to start at the closest end to the functional group. We don't want to start over here on the left as a 1 and then 2, 3, 4, 5, 6, 7, because that would give the functional group for alcohol the highest number. We want to give it the lowest number, just like we did in the previous video with the alkyls. So we want to start with carbon 1, carbon 2, carbon 3, carbon 4, carbon 5, carbon 6, carbon 7. So we know that this is going to be an ane because it's all single bonds, right? So we know it's going to be an ane, alkane, and it has 7 carbons in it. So the prefix meaning 7 is hept. So we know this is going to be a heptane. But at the beginning of it, we have this alcohol functional group, this OH group, coming off of the first carbon. So we're going to drop that E from the heptane, and we're going to add the OL, the suffix here that we have. So it's going to end up heptanol. All right, now let's do the carboxylic acid, the second one down here. Okay, carboxylic acid is always going to be on carbon number 1. It needs to be on the terminal end, as I went over before, of the molecule. So, and we're always going to make this carbon number 1 because we want the functional group to have the lowest number possible. So there's carbon number 1, carbon number 2, 3, 4, 5, 6, 7. It's heptane again. So we drop that E from the heptane, and this time we use the ending ic acid for carboxylic acid. But this time we're not going to do heptanic acid. We're going to do heptanoic acid. We're going to put that O in there since it doesn't have an O in there already as the connector vowel. Heptanoic acid. Now let's go down here to the third one, to the ketone. Now the ketone ends in one, O-N-E. I know it's spelled one, but it's pronounced own, ketone. So the one, O and E, already has an O in it, so we don't need two O's. We don't need the connector O because it's not ketone, it's just ketone, because it's not ketone, it's ketone. So we don't need an extra O, it already has the O there. So this is going to be carbon 1, carbon 2, carbon 3, carbon 4, carbon 5, carbon 6, carbon 7, carbon 8. So this is an 8-carbon chain. So the beginning of that is oct, and it has all single bonds, so that's an octane. But then we want to drop that E on octane and replace it with the one ending to let us know that there's a ketone there. So octanone. But now we need to tell you where that ketone is coming out, is sticking out from along the carbon chain, which is carbon number 4. So we're going to go 4-octanone. So we just know that the 4 is talking about the ketone. Now, ester is a little bit different. Ester, instead of just putting ER at the end of it, we don't do that. We go 8. And you can think of it like I went to Easter at my family's and I ate too much candy, or I ate too much Easter dinner. Okay, so I ate too much at Easter. So for an ester, we're going to use the ending ATE, and then we're going to use that O as a connector vowel. But there's one more difference with ester. Now, do you notice that this ester functional group is right smack dab in the middle of this hydrocarbon chain? Well, now what are we going to do? Because we don't just go 1, 2, 3, 4, because this doesn't count as a 4 because this isn't a carbon, this is an oxygen. And we don't go 1, 2, 3, 4, but then you run into the oxygen again. So what should we do? All right, so what you do for ester is that you always look at the single bonded oxygen, the oxygen that's interrupting the hydrocarbon chain. Okay, in this hydrocarbon chain, you start here, and we start numbering the carbons 1, 2, 3. So that's going to be your alkyl group. That's going to be your functional group. We're going to treat that like an alkyl hydrocarbon functional group. This is going to be your alkyl group. So we're going to treat this like just a regular old hydrocarbon alkyl group. And there's 3 here, right? There are 3 carbons. So the prefix for 3 in alkyl groups is prop, right? It's a propyl group. So we're going to have that propyl there. And then we're going to go on the other side of the ester functional group, the side with the double bond to the oxygen, and we're going to start numbering the carbons from this carbonyl carbon right here. So this is 1, and then 2, 3, 4. So the prefix meaning 4 is bute, and that would be the butane. That would be the parent chain, the hydrocarbon parent chain. No matter how many, for ester, no matter how many carbons are in this parent chain, the parent chain is always on the side of the double bonded oxygen. And no matter how many carbons are on the side of the interrupting oxygen, that sandwich oxygen, it's always going to be the alkyl group. This is the exception to normally make the parent chain the longest chain. This is an exception. So we have propyl butane, but we have this this ester group right here. And so we're just going to drop the E in butane and replace it with O8 because I ate too much at Easter. So we're going to have propyl butane O8. And you don't need to put a number here saying that it's carbon 1 on the parent chain where the ester is, because it's always carbon 1 on the parent chain where the ester is. That's why you always make the hydrocarbon chain on the side of the double oxygen bond always is the parent chain. So we can just automatically always assume that that's going to be carbon number 1 on the parent chain, this O8 suffix meaning ester. Now ether is also a little bit different, because what we're going to do is we're going to find the parent chain on the ether, which is going to be the longest chain. It's almost always, the parent chain is always the longest uninterrupted hydrocarbon chain that you can find, with exception for the ester, what I just told you about to do for ester. But other than ester, we're just going to find the hydrocarbon chain with the longest number of carbons. So this is 1, 2, 3, 4, and this is 1, 2, 3. So the 1, 2, 3, 4 wins. It has the longest parent chain. And of course, the carbon number 1 is the one closest to that oxygen. And so since it has the interrupting oxygen, we're going to use oxy as the ending to this. So this parent chain, 1, 2, 3, 4 carbons, so that means it's butane. So that means this part of the hydrocarbon chain over here on the right side, 1, 2, 3, is the alkyl group. So 3 is propyl, so propyl butane. But instead of normally dropping the E in butane and going butanoxy, right, we're not going to do that. As I said, ether's another exception on naming this. We're going to put the oxy and replace that YL with the oxy ending. Instead of putting the suffix on at the end of butane like we normally would, we're going to put the suffix on the end of the alkyl group instead, and we're going to drop that YL. So this is going to be propoxy butane. And we don't have to put a number on here because it's always, the parent strand always begins at 1 on one side of the interrupting oxygen, and the propoxy means it's the alkyl group on the other side of the interrupting oxygen, the 1, 2, 3. So this would be propoxy butane. So this is some things on just tips on how I remember this stuff. So alcohol, the ending is OL because alcohol ends in OL. And what's the alcohol functional group? It's an OH because OH comes right before the OL in alcohol. So alcohol ends in OL and because it has an OH. Now, carboxylic acid, we end in ic acid, but we put the O there. The O is the connector. Ketone has one double bonded oxygen. So one at the end of ketone, the word one. Now we pronounce it own, like you own something, but it's spelled one. So that just helps me remember that the ketone gets the ending one because it has one double bonded oxygen. Now, as I said before, I ate too much candy on Easter, so 8 is the ending for ester. And of course, we put the little connector vowel there with O. And then the ether, remember I said either or, because we have to have this. Here's the rest of the molecule. We have or right there, so either or. So oxy, we put oxy for the oxygen, the interrupting oxygen, that makes it an ether functional group. Knock, knock, who's there? Interrupting cow. Interrupting cow, moo! So the interrupting oxygen gets the oxy suffix. So here are some do's that you want to make sure you remember, with the exceptions of ester and ether, but do count the substituent carbon on the parent chain. So here's the carbonyl carbon on carboxylic acid. You do count that, and that's counted as number 1. And so here's the second rule right here. Count that carbon of the terminal end of the substituent as number 1 on the parent chain, and then 2, 3, 4, 5, 6 as you're going away from it. Now, treat the longest continuous carbon chain as the parent chain. So the continuous carbon, well, for ketone, it's going to be the whole thing because there's no interrupting oxygen in the middle of this. The oxygen veers off in the double bond. But like in ether, we go to the longest chain, hydrocarbon chain, before it gets interrupted by this oxygen, and that's going to be the parent chain. So we count 1 with the closest carbon and increasing numbers as you move away from it. You treat the shorter continuous carbon chain as an alkyl substituent. So this would be a 1, 2, 3. That's your alkyl. That's your propyl. That's your alkyl group. And finally, give the functional group the best priority when numbering the carbons of the parent chain. And by priority, I mean the lowest carbon number. Okay? So now that we've gotten that out of the way, what do we do in cases like these? Like, let's look at this first one right here. As you can see here, this has a carboxylic acid group on it in the front. But what else does this molecule have? It has this double bond here to it as well, right? So when we go to prioritize, who goes first? Which one do we prioritize first? We know the carboxylic acid has to go on carbon number 1. So that's kind of an easy peasy. But does it really need to go on carbon number 1, or should it go on carbon number 7? Because we need to prioritize this double bond first before the functional group. Or is it the other way around? Do we need to prioritize the functional group getting the lowest number carbon on this hydrocarbon chain? And then also in the second one here, we have another carboxylic acid right here on the 1 carbon, but we have an ethyl group over here on the 4 carbon. And then down here in the last one, we have the carboxylic acid right here, but we have a ketone right here. This is a ketone. So which one gets priority? Which one gets the lowest number carbon? Well, what you have to remember is the priorities of whoever gets the lowest carbon. The first priority is the functional groups. So, carboxylic acid would have priority over anything else getting the lowest carbon number. Okay. And then after that's taken care of, number 2 are the doubles and triple bonds. So then we're going to do the double bond here. And here's carboxylic acid down here. Here's functional group down here. And then after the doubles and any doubles and triple bonds you may have, then we turn to the alkyls, which is this ethyl group right here. So we're going to do this ethyl group is going to be the third in priority of getting a low carbon number, only after the doubles and triple bonds and after functional groups like this carboxylic acid. Now, this last molecule at the bottom of the page here has, again, a carboxylic acid group to it, but it has another functional group to it. It has the ketone. And so in that case, well, we're prioritizing the functional groups, but these are both functional groups. So how do we know which one goes first? Which one gets prioritized first? So prioritizing functional groups is all about redox. And that's, if you don't remember, that's oxidation and reduction. Now, remember, oxidation is not about oxygen. It has nothing to do with oxygen. It has everything to do with losing and gaining electrons. And what we mean by that is, I'm not talking about something getting positive, losing an electron and turning it into an ion per se. What I'm talking about is a lot of times if you have, say you have a carbon right here, and then you have this double bonded to an oxygen. Remember on the periodic table, the trend of electronegativity gets bigger as it goes up and to the right. So the more up and to the right an element is on the periodic table, like for instance, oxygen, the more electronegative it is, which means it just sucks up the electrons from the carbon and from that double bond until this oxygen is partially negative and this carbon is partially positive. So it doesn't have to turn it into a whole ion. It just has to suck enough electron juice up to itself to where it's just a little bit more negative, and the carbon it's taken it from is a little bit more electropositive. So if you remember the saying oil rig, you can remember which is which, because oxidation is loss, reduction is gain. And I know that sounds counterintuitive, right? If it's reduction, shouldn't that mean it's reduced so it loses electrons? No, because it's gaining electrons. The reason why it's reduced is because it becomes more negative. So that means its charge is reduced to a more negative electronegativity. And so that's why it's called reduction. So remember oil rig and these functional groups, priorities in these functional groups is all about the oxidation process. The oxidation, and that is if a carbon, when the carbon loses an electron, then it's going to be more electropositive down here at the carbon and electronegative up here at the oxygen. And so anytime you have a carbon with an attached heteroatom, and a heteroatom is just anything besides carbon and hydrogen that's an organic atom. So an organic element, anything but carbon and hydrogen. That means oxygen, phosphorus, sulfur, things like that are all heteroatoms. And so the rule of thumb is the more heteroatoms you have attached to a carbon, the more that molecule is oxidized. So if you have, let's say we have a carboxylic acid, you see how there are two heteroatoms attached to this carbon right here. Here's the carbon, but it has one oxygen, two oxygens attached to it. That's going to be more oxidized and more of an oxidized state than, say, just a ketone, which is just the carbon with the double bond to the oxygen, because this one only has the one oxygen attached to the carbon, whereas this one has two oxygens attached to the carbon. So both of these oxygens are sucking electronegativity from that carbon and making that carbon partially positive. So the more heteroatoms that are attached to the carbon in that functional group, the more of an oxidized state it's going to be in. And so the more oxidized it is, the higher priority it gets. So of course, the carboxylic acid with the OH group and the carboxyl group on it is going to always take priority to get the lowest carbon number in that chain over, let's say, the ketone. This is going to always take priority and get a lower carbon number in the chain than anything else. So this is the highest you can get. This is the most prioritized you can possibly get out of all the functional groups, is the carboxylic acid. Now, say you have this carbon is attached to, let's say, an OH group, okay? But this functional group, and I'm just pulling these out of the air just to make a point, and this functional group is attached to, say, nitrogen. Then what would happen is that we would have to look at, because see, both of these functional groups have a heteroatom attached to the carbon, right? So which one is going to go first? Well, you have to look at the periodic table and which one is the most electronegative, which in this case would be oxygen, goes first. Because nitrogen comes before oxygen on the periodic table, and the electronegativity trend goes up and to the right. Now, so first priority is the oxidation state. How many heteroatoms are attached to the carbon? If you have the same number of heteroatoms attached to the carbon, but they're different heteroatoms, you have to pick the one that's most electronegative. And then if you still have to pick between something, it's going to be the position on the hydrocarbon. So the ends, if the functional group is at the end of the chain, then that's going to come first. That's going to be more of a priority than, say, something in the middle of the chain. Okay, and one more. If you still have functional groups to pick from, if all those three qualifiers did not help and you're still playing tug of war deciding between two different functional groups, then it's going to be the number of bonds on the hydrocarbon. Then it's, if you have to pick from something like this, an OH with a double bond there versus something without a double bond, but it's the same thing otherwise, then you're going to pick the double bond over the single bonded one. And you're going to pick the triple bond over the double bond. So it goes triple, then double, then single is the bottom priority. So now that you've kind of got the gist when it comes to naming hydrocarbon chains with functional groups, now that you kind of got the gist to kind of a sneak peek of how to do this, my next video is going to be a full rundown of the entire list of functional groups and how to name them. If you are rusty on just naming your simple alkanes, alkenes, alkynes, then go back to my previous intro to organic chemistry videos on naming. But otherwise, check out my next video. I'll come out with a full rundown of the entire list of functional groups and how they fit along the lines of carbon chains.